Okay, folks, here we are at section 12.3, studying a really cool concept called Kernel PCA, which is a nonlinear extension of PCA. Now, I've only really learned about Kernel PCA in this past year, and I've never used it in real life, so we're kind of like learning it together. But I think it's it's a very interesting idea itself of how to expand our dimensionality reduction techniques so far to, into a nonlinear setting, and we'll see why we might want to do that later. Another reason why it's cool to know about is that some of these other dimensionality reduction techniques, the nonlinear ones, some like, for example, I think we'll talk about them at the end of this chapter, like locally linear embedding and isomap and others, can be thought of as kernel PCA, but with different kernels. So I'm always on the lookout for ways of, kind of simplifying, instead of learning like 10 different things, just learning one concept and tweaking one of the parameters. And kernel PCA can be kind of a unifying framework to understand a bunch of techniques, including PCA, but then in nonlinear versions of that as well. So it's kind of good to know about from that perspective. Okay, so let's get into it. Now the section is actually quite, there's a lot of like derivations in it, which are kind of pretty straightforward. But essentially the big picture is just going to be that we want to, for whatever reason, we want to actually do our PCA in a nonlinear feature space. So all the simple math we're going to do here is going to be kind of targeted towards that. So hopefully it won't be too you won't get lost in the details too much. Let's just kind of go through and kind of have a look at what we're going to be talking about. So the main idea is that we've already discussed PCA before, and here PCA comes down to figuring out the eigenvectors of a covariance matrix. Well, essentially what we're going to do is we're going to say, well, what if we wanted to do PCA not in this original data space, but after doing a nonlinear transformation? So maybe the very first thing we should highlight is this kind of nonlinear transformation there. Okay. And why we might want to do that is kind of shown in this picture, where, yeah, you guys can see it now. Okay, that's good. So the idea is that, what if your data is kind of lying along? So, well, let's back up a bit. So like normally, in the normal PCA setting, let's assume the data is centered. You have your data, and let me color it. Okay, so you have your data is, it's, as we saw before, you can kind of view it as essentially lying along some linear subspace with some noise on top, right? So that's kind of what we have in the normal PCA setting. Well, what if in real life you're often not going to be in that situation? So what if your data is actually kind of living along, some kind of a curved curved surface? Can you still do PCA that way? And one natural idea might be to say, well, what if we just uncurled it? So what if there was some kind of transformation that would allow us to uncurl this data and then get it into the setting that we want for PCA, and then we do PCA there, and then we can maybe like project back and figure out where what the PCA projections are in our original space. And that's basically the idea here. That's one motivation. You can kind of think about it that way. So that's going to be kind of the guiding idea. The only kind of not a problem, but kind of sometimes actually kind of not a bug, but a feature is that in this setting maybe it's possible to go back and forth. So you could even consider like maybe like drawing this line here as your kind of first principal component and kind of doing the whole thing in both directions. In many of the common kernel PCA settings, you won't necessarily be able to go backwards for and draw this vector, and we'll see why. And that will be related to the fact that this projection you often be taking your data and projecting it into a higher dimensional space. And so then when you draw this line, the projection of that line, which is going to go somewhere in that high dimensional space, it might not have a kind of a well-defined projection back into your original space. So like, imagine embedding kind of a line or a string into a 3D space, and then now taking some arbitrary point in that space, being like, well, where does it project onto the string? Well, it might not project anywhere. So that's kind of the difficulty. But we'll kind of get into that. But I think this example here is a good motivation that'll kind of get us most of the way without having to worry about these other issues. So you want to you want to essentially kind of unwrap your data, perform PCA, and then maybe project back. And that's kind of what you can view it from that angle. So we're going to be basically doing that. We're going to find some interesting relationships between the eigenvectors of that feature, of the feature projections, etc. But all the math is fairly straightforward, and then at the very end we'll kind of deal with some of these technical details of like what if the features are not centered, and then we get this kind of cool picture at the end where we look at some data we have here that we can't necessarily separate in these original spaces, but if we actually project the data into higher dimensions, then it actually becomes kind of more. It actually kind of does pick up the features we're interested in. Another we'll touch on this, but like another classic example I've seen of like showing why you might want to do kernel PCA is let's say you have your data, and we're gonna PCA is unsupervised learning, but let's just say you have your data, you had here's one set of features, and then there was another band of data out there. Right, here's kind of a now if you did normal PCA on this, it wouldn't be very helpful, right? Because it would just, one, there isn't, let's say there isn't kind of so much directionality, so you would get some, this would be one PC, this would be another one, you could rotate them, etc. But that's not the key problem. The problem is that they're not very meaningful, right? Like if you project your data along, these two vectors, it's not very meaningful. It'll essentially give you the same thing as you already have, but rotated. However, what if you could, what if you had a nonlinear projection that could, for example, extract the radius, right? So you would kind of take some point and maybe you would like map it to, that would be like one of your projections. Then all of a sudden, what you would get is you would get maybe, all these red points would be kind of showing up at one radius, and then your green points would be up at another radius. And now you can then feed that into some classification process downstream and be able to separate those two examples. And that's kind of what's going on here. So we'll kind of touch on that. Like essentially the idea is, often in, it will be many times the case that your data as it arrives is not going to be in the most useful format, and you might want to do a nonlinear transformation on it before you do the further processing. And kernel PCA is kind of one way, one approach to doing that. And we'll talk about how where the kernels come in, and all of those things. So okay, so I think let's just enough chatting on. Let's just get started, and things should hopefully become clear as we go. So let me make sure you guys can see this. Okay, perfect. Okay, so let's start the reading. Chapter 6, which we haven't covered yet, but you can essentially read this in kind of a standalone way. How the technique of kernel substitution allowed us to take an algorithm expressed in terms of scalar products of the form xt x prime and generalize the algorithm by replacing the scalar products with a nonlinear kernel. Okay, maybe we do need a bit of a word on kernels. For the sake of what we're going to discuss here, you can think of kernels as kind of like as similarity functions. So, a kernel will be some function that's going to be symmetric, will be, I don't want to say it has to be necessarily positive, but for what we're going to discuss here, it doesn't have to be positive, but it will be symmetric. So the kernel of x and y, and it is going to just report a single number r that's going to give you some notion of similarity. And, k of x is going to be, k of xy, etc. But you can just think of it as, for what we're going to discuss here, it'll just be a notion of similarity. And we've already kind of worked on these before. So kind of an example of a kernel is just this, the basic linear kernel. You guys can see this, which is just the overlap. And there you can see that it's not necessarily going to be positive, but it is symmetric. And so, but you can kind of generalize this, and this is like you can have other notions of similarity. And this is kind of a really powerful idea because it will allow you to compare things that you normally, maybe you can't, there's no obvious kind of vector space embedding of them. For example, let's say you want to compare words, like similarities of words. Well, it's kind of unclear a priori, how to compare them. Maybe you want to compare like different animals. Like it'll be very unclear how to embed them into like some vector space and then form the dot product. But you might actually have some like some values. You might, if someone asked you like how similar is a dog and a cat, maybe you could actually provide a number without having to go through this intermediate step. So the idea with these kind of kernel algorithms is to essentially allow you to work, to do everything in terms of those kernels, which are kind of often easier to work with. And it'll turn out that it is the case that these kernels will correspond, I think in a one-to-one manner. You'll have to look up the details, but they'll correspond to a mapping of your data points into a feature space and then doing the projection, do this linear projection. But the cool thing is that most of the time, well, in all of these cases, the whole idea of the kernel aspect is that you don't actually have to deal with those feature spaces explicitly. So, this kernel will correspond to a mapping that takes X to, some Hilbert space. And the kernel then itself will become, you guys can see this, k of xy is equal to phi of x. Well, I don't want to do transpose. It's going to be a, an inner product on that Hilbert, you guys can't see this. I will just do that here. And this will correspond to phi of x, the inner product that you get in that Hilbert space of those features. But the whole idea is that these features can be very high dimensional, infinite dimensional, but actually you won't have to work, in all these algorithms, you won't have to work with the features. You can actually do things in terms of the kernel itself. That's kind of a really huge advantage. And so, kernelization is all about turning these algorithms and rewriting them in a way that only deals with the kernels, not with the features. And that's, what we're going to be doing here. Okay, so a little bit of just little tidbits you need to understand this section. Okay, so consider a data set X of n of observations, as usual, in a space of dimensionality D. In order to keep the notation uncluttered, which will assume that we have already subtracted the sample mean. So we're gonna, these are all mean zero, so we can just write our covariances in this way. We don't have to mean subtract. We'll have to deal with this mean subtraction at the end of the section. But it's just, it's not a big deal, and it's not kind of what this section is really about. Okay, the first step is to express conventional PCA in such a form that the data vectors appear only in the form of the scalar products. He doesn't actually do this. In my online notes, maybe I'll just do this as well, so just for completion. But again, so this is now, you want to write PCA in terms of these kernels, right? It's kind of the linear kernel. Okay, so recall that the principal components are defined by to be eigenvectors of the covariance matrix, right? That was the whole point, and here's the covariance matrix, and they're normalized. Okay, so we've already covered this before. Now is kind of the whole point of this section. Now we now consider nonlinear transformation into an m-dimensional feature space. So I think I need to kind of highlight this m-dimensional feature space. Okay, and again, remember it's the feature space idea is good to keep in the back of your mind, and maybe when you're doing kind of these theoretical calculations. But in real life, the whole point is to not actually have to compute these features, these projections in the first place, because it could be complicated, infinite dimensional, etc. Okay, so that each data point is thereby projected into a point phi of x of n. Okay, we can now perform standard PCA in the feature space, which implicitly defines a nonlinear principal component model in the original data space. So this is essentially the main idea of this section. In the feature space, and which implicitly defines a nonlinear principal component model in the original data space. That's what all of this is about. Okay, and we just kind of talked about it in this figure. Okay, now for the moment, let's assume the projected data set also has zero mean. And we can talk about what happens when that's not the case. The m by m sample covariance matrix, so m, it's not d by d anymore, it's m by m because these features are m-dimensional, is given by this, right? Just the same old covariance formula. And it also has, eigenvectors just exactly the same way, right? This is just PCA. Okay, now our goal is to solve this eigenvalue problem without having to work explicitly in the feature space. I need to, again, highlight this. This is always the goal, right? With the kernel methods, you want to do whatever it is you're doing. You want to do it, solve your problem, in this case, an eigenvalue problem, but without having to actually compute anything in the feature space, because the feature space could be complicated. So let's highlight that. Okay. Now, from the definition of C, the eigenvector equations tell us that VI, so this thing, right? We just literally plug in C into here, and that's all. That's what we get, right? So we've just kind of split it up. So it used to be split up this way. We just put the braces now over there, and now you notice that. And so we see that provided lambda is greater than 0, the vector vi is given by a linear combination of the phi of x of n, right? So we can write this vector vi as being, up to scaling, the projection of the feature mappings of each of the points, onto itself, which will be, some unknown value. And we're going to figure out what that value is in a second. But for the moment, you can just say, well, this is going to be some constant that'll depend on n, and it'll depend on I, which will be the corresponding eigenvector. Okay, so that's what we have here. I think I can erase. Don't need any of that. Okay, great. So now we're just gonna do a little bit of algebra. So we're gonna substitute this back. So we're gonna replace. So this. Let me actually highlight this point. I think this is actually quite useful. Okay, so now we're just going to substitute this representation of the eigenvectors. We're representing in terms of the feature mappings. It's kind of cool actually, because when you have data, you can a natural thing is to do PCA or find the covariance matrix, and get the eigenvectors and represent the data in terms of those eigenvectors, and there's nothing wrong with that. But here what we're doing is we're actually representing the data in terms of, points in terms of the data itself. So we're saying, in this particular case, we're going to represent the point as in terms of, well, what do we have? Well, we just have data points. So why don't we try to represent everything? Let those data points be a coordinate system and represent whatever we're interested in, other points in that space in terms of the data points themselves. So it's kind of an intrinsic coordinate basis, which will be over complete. So there might be lots of ways of representing a given data point. And what we'll see is that, our method here is going to pick out one of them. Okay, so now we're just going to put in this. So we're going to say, well, we know it's going to be this linear combination. Let's put it back in. So we're just going to. So this is C. This is. I can just write that down. So this is just C. This is V, and this is VI, and this is VI again. Okay, so this is just our eigenvalue equation. But again, there's no kernels yet. So now what we're going to do is we're just going to multiply. We're going to do kind of a. So we're just going to do this projection, multiplying both sides by phi of x till t. Okay, so if we do that, then all of a sudden we'll have like a phi of xl transpose hanging out there, phi of xl transpose hanging out there. Well, this, again, we're doing this. It's a scalar product of these features. Well, what is that? It's just the kernels, right? Right, because now we're going this has now combined into this, so this is gonna give us, I'll just call it ln. This is going to be knm, which is what we have there. So that's exactly where the equation comes from, and so we can just write it in matrix notation, right? If you just look at this is just a matrix multiplication where the elements of k, let's call it ln, is equal to k xl xn. This is just a number. Okay, so we just got this matrix that's being filled with these numbers. And so this equation is just the same as k squared, right? We just bring the n to that side, k times a, and k times a. All right, so now what we can do is we can just solve, what your natural point here is just, well, let's just multiply by k minus 1, which is effectively this point. You have to just be careful about the solutions won't be exactly the same, because the solutions we'll get up here will also correspond to the AIs where k, that are in the kernel. Now this is a different kernel. This is the AIs that make ka 0, whereas here those won't necessarily be solutions, but those don't actually make a difference. So we can find solutions for AI by solving the following eigenvalue problem. So where we multiply it by k, even though k might be non-invertible, strictly speaking, in which we have removed a factor of k from both sides. Note that the solutions differ only by eigenvectors of k having 0 eigenvalues that don't affect the principal component projection, right? So it's going to be possible now that we're going to have eigenvectors that have 0 eigenvalues, but, well, they're not going to matter for what we're doing. So all we care about are the eigenvectors that correspond to positive eigenvalues, and for those, they will be also solutions to this. So that's essentially what he's talking about. So let's highlight Differ only, but okay, right? So you always have to be careful when you're inverting things, and it turns out that if we do the natural thing here and invert, pretend everything's invertible, the vectors that we get out of that will be the ones we care about anyway. All right, so now we've got this equation. Finally, we just want to know, well, what is, there's a kind of a length ambiguity, as there always is with these eigenvectors. And so we just use the original fact that our VIs are supposed to be unit norm, and we can solve for what the norm of these AIs are. So, this you just divide it. The norm, the squared norm is just 1 over lambda I times n. Okay, so that's it. And now we're basically done. So having solved the eigenvector problem, the resulting principal component projections can then also be cast in terms of the kernel function. So now the point here is you want to project, you want to figure out if for a given point in your original space, how much does it, what is this projection onto one of your eigenvectors in the feature space. So notice you've projected feature space, and now you are doing the standard PCA thing and projecting onto an eigenvector. Well, again, this expression comes to your rescue. You just plug it in, you see? So there it is. And that was the expression for VI. You plug that in and you see that it actually is the projection. Again, the kernel function comes in. And so what that's telling you is, let's say your point is in your feature space. So let's say these are like, here is like, x1, x2, x3. And now this is like, let's use a different color. Let's use blue. So this is your point X that you care about. And you want to know, well, how much does it project onto, what is the projection onto, let's say, the first principal component in the feature space? Well, each one of these points is, the kernel function kind of gives you how much each of your actual data points influences the answer. And you do a weighted combination of the contributions from each of those data points according to these weights that are coming from your eigenvalue equation. So that's kind of what this expression here says. So you can kind of express these projections in terms of the kernel and these values that you already found. And so you can then solve this equation, and we'll see a picture of that in a second, to see like what is the set of points in your feature space for each one of these eigenvalues that has a certain certain projection. So let's for example, if we go back to this figure, that's exactly what they've done. So here let's zoom out a bit, and I'm just going to call this let's say this is like, you guys can see. So there's like phi x transpose v1 is equal to 1, let's say, I don't know, maybe 2, 1, minus 1, minus 2, whatever it is. Well, you can actually then solve that in the original space. You can say, well, let's call x1 equals the set such that phi x transpose vi is equal to, v1 is equal to 1. Right, and so that would be the So that would be the projection of, that would be the back projection of like this point of this line all the way over here. Okay, and so on. So you can always do that. So let's go. Yeah, there we go. Okay, cool. Yeah, there we go. So in the original, d-dimensional X space, there are d orthogonal eigenvectors. Hence, we can find at most d linear principal components. Now, now we've kind of projected into a higher dimensional space. So the dimensionality M of the feature space, however, can be much larger than d, even infinite. And it doesn't have to be so exotic. So we'll, some kernels, for example, there's a kernel that measures similarity by kind of in a Gaussian way. So it measures the distance, the square distance, and then it applies, negative of that, the exponential. Well, that corresponds to an infinite dimensional features. So it's not like these are kind of an exotic thing that the features are infinite dimensional. And thus, we can find a number of nonlinear principal components that can exceed d. Right? In principle, M can be very large. and much larger than your original space. Note, however, that the number of non-zero eigenvalues, right? So not eigenvectors, cannot exceed the number n of the data points, because even if you have more dimensions than data, the covariance matrix in feature space has rank at most equal to n, right? So essentially that's saying that, okay, what is that saying? So let's say, in this case, I'm going to take some linear data. So let's say like some data that looks like it's kind of falling along this line, and then I'm going to apply this squared projection, and it's going to now live in this kind of two-dimensional space. So here, dimensionality of the data has gone up, so that's good. The number of non-zero cannot, yeah, but okay. So it says, note, however, the number of non-zero eigenvalues cannot exceed the number n of data points, because even if the dimensionality of feature space greater than n, the covariance matrix in feature space has rank at most equal to n, right? So now you can imagine, you project your data into your m-dimensional space, and now you have this like, very long, this is like m, and now you have n, and now you're going to compute the covariance. Well, the covariance is going to be, the number of eigenvalues, non-zero eigenvalues, the covariance matrix of this data. This is your data x, actually 5x. Well, it's going to be at most the smallest one of these two, right? The smallest of m and n. So when you form the covariance matrix, you'll see that that's the case. So this is reflected in the fact that the kernel PCA involves the eigenvector expansion of the n by n matrix K. Okay, so even though your features are going to be, potentially very high dimensional, the number of non-zero eigenvalues, you can always define more eigenvectors if you want, but you're going to be limited by n. Okay, I think you guys get that. Okay, now finally, we're just going to talk about kind of a slightly technical point but important points. It's not it's kind of as in just a detail that shouldn't take away from the main message of the section, but we need to deal with it when we're applying this. Okay, so we've assumed that the projected data set given by has zero mean, which in general will not be the case, right? Now we can't simply compute and then subtract off the mean, because we want to avoid working directly in the feature space, right? So we can't just kind of do this, right? Like compute the features and then like subtract the mean from them. The whole point is to avoid having to work with features. So let's highlight that. We cannot simply, yep. So the idea is, can we do the same thing in formulate the algorithm purely in terms of the kernel function, right? That's the whole point. Okay, so let me highlight that. I think it's important. Okay, the projected data points after centralizing are given by this, right? The tilde is going to mean centralized. Okay, so all we do is we're just going to write this out in terms of, so this is the kernel of the one we want to work with, where the data is already centered, and we just want to be able to express it in terms of the kernels of the data that we already have. So all we do is we're just going to write this out and then just collect terms. That's all there is to it, right? So we're going to multiply n by m. Well, because that's that. So now you just take this for x of n, do the same thing for x of m. You get a bunch of terms coming up, blah, blah, blah. Okay, and then when you look at them, you're like, oh, this is just the kernel for the features we already have, the uncentered ones. There it is again, there it is again, and there it is again. So all these terms multiplying, they just are kernels. And you can then just write this in, compactly in matrix notation as this expression. The only thing is just minor detail, which every element takes the value 1 over n. Right, so that's what that is. So, so 1n is defined as 1 transpose over n. Okay, and you can just work that out. It's a very simple computation. So the whole point of that was, thus we can evaluate k using only kernel functions and then use k tilde. So we can just use k tilde. You can compute k tilde the way we have here, and then just everything else in the section goes through. Note that the standard PCA algorithm is recovered as a special case if we use a linear kernel. We already talked about this. And figure 2 shows an example of kernel PCA applied to synthetic data set with a Gaussian kernel. So this is kind of a common kernel that's used, and this corresponds to features that are infinite dimensional, but again, you don't have to deal with them because you can just use the kernel function throughout. And the lines correspond to contour lines along which projection onto the corresponding principal components is constant. So let's have a look at this. This is kind of a cool picture. Yeah, let me just erase all of this stuff. And you guys can see this. Yeah, great. Okay, so all it is, okay, so we're looking at, so we have data. This is in our original space. So we have three points. And we've used kind of these radial features saying that the similarity of the points is dependent on, yeah, it kind of falls off in a kind of a spherical way. So this is what we have here with some width. And that kind of seems like maybe the right notion of similarity to use in this space for this data, right? Because you got these kind of 3 clusters, and you can see that in fact, like, you know, again, if you wanted to do PCA in this space, it wouldn't be particularly useful because, you know, I don't know, let's say if you did it, then you end up with kind of these 3 clusters that maybe, I don't know. Let's just say, yeah, let's just look at what kernel PCA does on it, and how it kind of seems to group, you know, seems to kind of group the various clusters here kind of in a more natural way than just a projection onto these components, which would essentially amount to kind of a rotation of the space. Okay. Yeah, I think, for example, sorry to be sticking with this, but like, let's say we found, I don't know, like the projection, we just did linear PCA on this space. You know, we'd probably find maybe one direction here, and then an orthogonal direction here, and then, I don't know, these guys would be, yeah, it effectively just corresponds to a rotation. So it's not very handy. Whereas we can see, so now the cool thing with the kernel PCA, and this is kind of what's shown here. So what each one of these plots, it's always the same data, always the same points, but we are showing the contour lines for one of the eigenvectors. So there's the first eigenvector, second one, all the way. And so what's cool about this, you can see that the first eigenvector seems to put a very large value on this particular cluster. It puts a very small value on that one, an intermediate value there. All right, that's determined by the colors. You can see the contours falling off. And then similarly, the second one, you know, you see it's kind of cool, right? The second one's kind of picked out. The second cluster really doesn't like this one, and maybe the cluster over here is intermediate. And then you can, you know, as you go on, you can see that for this third eigenvector in feature space, when you map it back, it actually seems to split this cluster a little more. It's kind of doesn't really care about those guys, and it's kind of this splitting going on, and kind of, so it seems like it's kind of found a representation of the data that's kind of more somehow faithful to it than doing kind of a linear separation, which is really quite cool. Okay, so I think, you know, very, very cool plot. It's going to show you what it's all about. And yeah, so yeah, we've already talked about that. Very good. Okay, so that's that. At the very end here, so one obvious disadvantage of kernel PCA is that it involves finding the eigenvectors of the n by n matrix K rather than the d by d matrix S of conventional linear PCA. And so in practice, for large data sets, approximations are often used. So one of the trade-offs. Okay, so I said now finally, we note that in the standard linear PCA, we often retain some reduced number of eigenvectors and then approximate a data vector x of n by its projection onto the L-dimensional principal subspace defined by this. Okay, so remember we did this before. So we had our data, and it was lying like this. This was all of our data points. Then we had this, and this was like the first principal component. We had like a data point maybe over here, and we said, okay, we're going to approximate it by its projection onto that direction. So that's kind of what's done here. So we're taking a particular point, we're projecting it onto however many eigenvectors we care about, and then expanding it, scaling those eigenvectors by that amount to get its representation. So that's just a geometric version of what we're doing here. Now the important point is that in kernel PCA, this will in general not be possible. In some settings, you might be able to do it, but the main problem is that you're going to be kind of embedding your d-dimensional data into a higher dimensional space, and the linear projections of your points aren't necessarily going to live on that d-dimensional manifold. So let's just go through it, and I'll try to draw a picture for you to make you see that. So okay, so to see this, note that the mapping phi of x maps a d-dimensional x space into a still d-dimensional manifold in the m-dimensional feature space. Okay, so the vector x is known as the pre-image of the corresponding point. Just a fancy word of saying, what is the inverse under phi of phi of x. However, the projection of points in feature space onto the linear PCA subspace in that space, the feature space, will typically not lie on the nonlinear d-dimensional manifold that describes your data space, and so will not have a corresponding pre-image in the data space. So let's see if we can kind of draw a picture of that to help you. So let's just say, okay, let's even stick in 2 dimensions. Hopefully, I'll get this across correctly. So here is our data. So we're going to call this x1 and x2. Okay, and so our data is going to be kind of lying along this. Okay, so now we're going to project, and I think we can still, let's just project still into the same number of dimensions. So this is kind of one-dimensional data that's going to be projected. And so after the projection, maybe we've managed to kind of straighten things out a bit. So now our data kind of maybe looks like this in our feature space, something like that. So this is notice this is still a one-dimensional manifold. So if your data is one-dimensional here, it's going to be kind of one-dimensional there. And now we're going to do PCA on it. So let's do PCA. I was like, oh well, it does fit. So there's there's our first principal component. Actually, just to make it a little bit clearer what's going to happen, I'm going to say that's the first principal component. That's going to be called V1 in that space. Now the whole point that he's trying to make is that if you've got one of your data points here or anywhere, and you project it onto this line, and you then want to project back, you want to say well, where does let's say phi minus 1 of that go onto my manifold? It won't necessarily be clear. Like in this case, maybe it might show up there, but the point is that it won't really show up on your data manifold. It's a bit more obvious. It's a bit more obvious when there's kind of 2 dimensions, and now you have like some 2-dimensional. Maybe it's kind of being projected now. Let's yeah. So again, yeah, it's hard to draw this. I think you get the point. So in 2 dimensions, you can imagine now you have your 2-dimensional surface, like a piece of paper, kind of curved, maybe less curved, and that's in the 3, 4 infinite dimensional space. And now you're going to project. Let me try that. Let's say this is kind of. You guys can see this. So this is going to be on our feature space. We managed to flatten it out. Okay, so now we figure out the linear subspace that captures the first 2 principal components. Well, there's going to be this gap, right? When we want to, this is where the data is supposed to live. Data lives on this on this 2-dimensional manifold. The projection you've got is off that manifold. So when you want to map it back, it's going to be unclear where you should map it back onto, because all your data, the place where your data lives, is no longer where that projection lives. Whereas in this space, you could kind of conceivably, that was a perfectly valid location. You're working in the data space the whole time. So I hope that kind of gives you the flavor of what the problem is here. That essentially is coming from the fact of this projection into a higher dimensional space, and the fact that your data lives on a kind of submanifold of that space, and so other points in that feature space aren't necessarily going to map back onto your data. So you can't necessarily do this kind of approximation, but what you can do is at least mark out in your feature space the locations, the contour lines that correspond to different amounts of projection onto those principal components, and that can be very useful, and that's kind of what's shown there. Cool. So I hope that was interesting. I find this kernel PCA stuff very, very interesting, kind of theoretically and conceptually. I haven't used it in real life, as I said, but I think it's really, really cool to know about. I think it's a nice kind of unifying approach to some of these dimensionality reduction techniques. So I hope that was helpful for you. Please let me know, as usual, what you think, whether whether you liked it, you didn't like it, maybe I did explain something incorrectly. Let me know. Always happy for that, so we can learn this stuff together. And yeah, so I think that's about it. Next time we're going to be talking about nonlinear latent variable models. So another kind of flavor of the nonlinearity that we've been working with in this section. So yeah, so I hope to see you then. Bye.